bootstrapping, a special type of sampling, and also we saw some of the statistical concepts. So in this class, we will continue some of the statistical concepts, and also we will learn about information theory. Learning about information theory is essential because we are dealing with a lot of data. So it is good to have some knowledge about information theory. So we will do these two things in this class. So in the first class, we saw that we are interested in looking at the relationship between the data. So we are interested in seeing how the variables are related to one another. For example, if you take the temperature outside and the chances of snow, how are they related? If temperature is high, the chances of snow are less. If temperature is low, the chances of snowing is high. So they are inversely related, or I can say they have a negative relationship. If one is high, other one is low. Supposing if temperature and the number of swimmers, if you take these two variables, when temperature is high, when the weather is very warm, the number of swimmers are also high. So they have a positive relationship. If one increases, the other one also increases. So covariance means when two variables have a specific pattern, whether they increase or decrease by a fixed multiple of amount, we call that they are covarying. For example, you have a variable A and you have another variable B. If A increases by 3, B will increase by 6. If A goes up by 2, B will go up by 4. If A decreases by 4, B will decrease by 8. So if you look at it, B is increasing or decreasing with respect to A by the amount of 2. So it goes up or down by twice the amount of A. So we can say B is co-varying with A. We can say these two variables A and B are co-varying. So if two variables are co-varying, we call that term as covariance. So we see how the relationship between A and B. So they are co-varying, and this concept is called as covariance. Covariance talks about the relationship between two variables, how they are related. For example, you can take this as x-axis and this as y-axis. If you look at these dots, these data points, if y is increasing, x is also increasing. So you can say there is a positive covariance. Suppose here also when y is increasing, x is increasing, but for the larger increase in y, there is only a smaller increase in x. So we can call this as weaker positive covariance. So if x increases, y is also increasing, it is positive covariance. If x decreases, y is also decreasing, it means it is called as a negative covariance. So when two variables covary, we call the term as covariance. Covariance is nothing but finding the relationship between two variables. So how I can express negative covariance? So when y is decreasing, x is increasing. So when y is decreasing, x is increasing by a small amount. So this is weaker negative covariance. So suppose imagine that you have data points like this. This is x, this is y. We cannot say a pattern here. So if X is increasing, we cannot say the increase or decrease in Y is inconsistent. So we cannot tell. Here also we can have another pattern like this. When X is increasing, Y is both increasing as well as decreasing. So there is no consistent pattern in it. So in this case, we call this as zero covariance. When there is an inconsistent pattern with one variable is increasing or decreasing, the other variable is inconsistent in its pattern, in its direction or with the relationship. So we call it as zero covariance. So Y is inconsistent in both magnitude as well as direction. Covariance essentially captures only the relationship between the variables. I can write a formula for covariance. Covariance between the two variables X and Y is given by summation I is equal to 1 to n, X of I minus expected value of X, Y of I minus expected value of Y divided by n minus 1. This is a formula for covariance. Covariance, what it does, it measures the degree to which two variable changes together. It indicates whether increase in one variable corresponds to an increase or decrease in another variable. But here, one information to be thought is that this covariance provides only the direction of the relationship. It says whether it is positive or negative, but it does not indicate the strength or magnitude of it, how much it is covarying. It doesn't tell the magnitude of the relationship. It's only the direction of the relationship is given by the covariance. It's a useful concept, but it does not take into account of the units of the two variable. When I mention units of the two variable, what I'm meaning is that, for example, if you take a guitar, there are number of variables in the guitar, like thickness of the wood, length of the neck, time with the note it resonates, tension of the strings. So there are lot of variables with respect to a musical guitar. So everything has its own unit. Thickness of the wood can be in millimeters. Length of the neck can be in centimeters. Time of a note can be in seconds. So everything has its own, all these are variables. We can, if you want to look at the relationship between them, they can give only the direction if you use the covariance. But we cannot essentially compare these two, because if you compare these two, they are two different units. So you cannot compare using covariance. So what is another parameter which we can use? It's called as correlation. Correlation is helpful to identify the direction as well as strength between the two variables. So it helps us to find the direction as well as strength on how these two variables are related. So, for example, if I draw this line, let it be X and Y. This line will represent the direction, and the dotted points there will represent the magnitude of the relationship between these two variables. If the dotted points are on the straight line, it means that there is a perfect correlation. This line, we can say that still it is positively, it has a positive covariance, but it has a weaker correlation. It is positive, but it has a weaker correlation. So when it has a perfect correlation, it is, we can say, +1. Correlation varies between -1 to +1. So in this case, the value of correlation is +1, strongly correlated. This is weakly correlated. So when the value is 0, when the correlation value is 0, we can say the correlation is low or weak. When the correlation is 0.5, we can say moderate positive correlation. When the correlation is perfect +1, perfect correlation. Perfect positive correlation. Similarly, for a negative correlation, when it is near to 0, we have a low negative correlation. When it is minus 0.5, it has moderate negative correlation. When it is minus 1, strong or perfect negative correlation. So if you have a data points like this, we know that X is not following a pattern, Y is inconsistent with to the changing pattern of X. So in that case, we have zero covariance. When we have zero covariance, we will also have zero correlation. Because correlation is just a scaled version of covariance. So when it is a scaled version of covariance, I can write correlation coefficient or just correlation as correlation with this formula. So covariance divided by sigma X, sigma Y, where sigma X is nothing but the standard deviation of X, sigma Y is the standard deviation of Y. So this is the correlation coefficient. So +1 refers to perfect positive correlation, -1 refers to perfect negative correlation, 0 refers to no correlation. Unlikely like the covariance, this correlation is not affected by the scales or units. So correlation standardizes the covariance. It is a scaled version of the covariance. It provides a unitless measurement, and also it provides both strength as well as direction of the relationship between the two variables. So if in our discussion, if you are using two variables, you're comparing the relationship between two variables, you can call this as simple correlation. Suppose if you are finding the relationship between multiple variables, among multiple variables, you call this as multiple correlation. Suppose you have multiple variables, a range of multiple variables, but you are interested only in looking at the relationship of only two variables, then you call this as partial correlation. There is one more term. So you have two variables and they are perfectly positively correlated or perfectly negatively correlated. Then you call them as linearly correlated variables, because all the points will lie on the line. If the variables described by any other value of the correlation, then they are said to be non-linearly correlated. They are perfect. If they are perfectly correlated, either it is positive or negative, it is called as linearly. Any other correlation is called as non-linearly correlated variables. So if all the points lie on the straight line, this is a positive correlation. You can see when X increases, Y is also increasing and all the points are lying on the line. So it is a perfect correlation. So I can write it as +1. This is a positive correlation. But all the points are not lying on the straight line. So this is just a positive correlation, non-linearly correlated. They are not linearly correlated. There's an inconsistent pattern between X and Y. Then this is zero correlation. So if you look at this one, this is a negative correlation. When X is increasing, Y is decreasing. And the points are not on the line. So they are non-linearly correlated, but negative correlation. The points are lying on the line and there is a negative correlation, negative covariance. So this is perfect negative correlation. Did you understand it? This means it measures only the direction of the relationship between two variables or multiple variables. Correlation means it measures direction as well as strength of relationship between the two variables. Correlation is essentially a scaled version of covariance. So why we are using covariance and correlation? To find the relationship between the variables in the data, we use covariance or correlation. If you are interested only in the strength, only in the direction, then we use covariance. If you want strength as well as, if you want direction as well as magnitude, we go for correlation. And we just saw the formulas for those things. So we have touched a few of the statistics concepts, but the statistics tells everything about the data. We have the data, we perform some statistical measures on it, but it may not reveal everything about the data. It may not reveal all the relationship about the data. It is a great place to start, but if you look at closely, we have to understand the data very well. We have to dig into the data. Just statistics will not tell everything about the data. For that, is my screen visible to you?
Yes, ma'am.
So if you look at here, so there are 4 data points. So all these 4 data sets are 2D points. They are not, what to say, these sets don't look alike. They are all different one. But if you put the statistic, they have the same mean, same covariance, same correlation, and the same straight line of it. Though they don't look similar, all the statistical values of these 4 data points are same. So it is called as Anscombe's quadrant. This is named after the mathematician who found this values. So though there are 4 different set of points, they don't look alike, but they have the same statistical measures. So what we can conclude from is that statistics does not tell everything about the data. We have to look into the data flow much more closely to understand the relationship. That is an example which we got it from Anscombe's. Is it clear? Any doubts? Okay. Now let's move on to something interesting. So information theory, we will look into the basics for the rest of the class. We will look into the basics of information theory. Why we need to learn information theory is that it tells us how to measure the amount of information in the data. Secondly, it also tells us how to compare the efficiency of different representations of data. The data can be represented in several forms. So which form is more efficient? We can learn that from information theory. So originally information theory was used to find the most efficient way to communicate a message electronically. It also gives us the tools for measuring how much we know about the data by converting it into a digital form. So for these reasons, we need to learn about information theory. So theory, everybody knows. So what is an information? Information essentially has two meanings. It is a one word, but it has two meanings. One meaning is used in everyday's language, information. The second meaning is a scientific meaning. So, so to send an information, we should have a sender and we should have a receiver. So the information is always sent from the sender to the receiver. Suppose if the receiver receives a new information, it adds to the surprise value of the receiver. So what is a surprise? Surprise is nothing but the gap between the expected event to what we actually learn. So surprise is nothing but the gap between the expected event and what is actually learned or what is actually present. So for example, if a doorbell is ringing, we open the door and we saw a delivery boy in the doorsteps. It is not so surprising. It is very little surprise because this is not an unexpected event for a delivery boy to stand on the doorsteps. Suppose if a gorilla is standing in the doorstep, it is very much surprising. So surprising is an unexpected event. We can say in other words also, is as an unexpected event. So let's take another example. Suppose you receive a message from an unknown person. When you open the message, you see the word thanks. So if you put a surprise scale from 0 to 100, when you see the message called thanks, you can rank it as 20. Somebody saying thanks is normal. Suppose you see a word called hippopotamus when you open the message. Until otherwise, you are working on animals. If you receive the message called starting with hippopotamus, it's a huge surprise value. You can rank it as 80. So second time, when I say hippopotamus for the first time, you would be surprised. But again, when we are repeatedly saying the same term, you will not be surprised. The surprise element goes with the most frequently with the most common usage. The surprise elements goes down. So, and the surprise element also has a context. So if you're working with animals, hippopotamus is not a surprise thing. So the context is very important. What is the context? Suppose you have a sender and a receiver. You are sending a information. That information is nothing but a piece of language. So both the sender and the receiver should know the language. Only if they know the language, they have a shared context of the language, we can send the piece of information to the receiver. If the receiver does not know the language, even if you send it, it is not going to be of any use. So the shared environment is called as context. The context is nothing but the general environment between the sender and the receiver. Want to be more formal, this we can call it as global context. There is one more context called as local context. So what is a local context? Local context is nothing but if you are sending an essay, in the third paragraph, there are some words. Those words were explained in the first paragraph. So the first paragraph essentially gives you the context for the third paragraph. Only when you read the first paragraph, you can understand the third words in the third paragraph. So they are essentially giving you the context, and this is a local context. Because locally, the words which are coming in the future, the context is given in the past paragraph. So it is called as the local context. The local context is made up only with the words that is preceded by it. So to describe the amount of surprise, we attach a surprise value to every context. So the surprise value can be assigned a number. So every word in the dictionary can be assigned, what to say? We can assign a surprise value to every word in the dictionary. If you scale these numbers, they should add up to 1. So what we have created is nothing but a probability density function. This probability density function, or you can call it as probability mass function, because that will be more appropriate when we are dealing with discrete variables. So the surprise value is nothing but a numerical value which is attached with every piece of data, so that we can measure the amount of surprise. Is it clear? And the second concept about the surprise is the most commonly used word. The most commonly used word will carry less surprise, whereas the less frequently used word will carry more surprise. Is it clear so far? So we started with the information, meaning of information. We understood what is surprise, and we saw what is global context, what is local context, and next we saw how to quantify the amount of surprise. In this class, we are not dealing with the mathematical concepts. We are just understanding the explanation behind the concepts used in information theory. We are not dealing with the what to say, formulas or mathematical explanation behind it. Next, what is a unit of information? Mass, kilogram is its unit. If you take time, second is the unit of time. So for information, the unit is bit. So the bit can carry either 0 or 1. So if I say 1000 bits of memory, which means that it can carry 1000 bits of information. So we store these bits in electronic circuits. So how do we measure information? So now we saw the unit for information, which is a bit. So how do you measure information? We measure it using a formula. So the formula has two terms. The first one is the text of the message. The second one is the probability mass function. So the formula contains two things. To measure the information, there is a formula which uses two things. One is the text of the message, and the other one is the probability mass function. This formula has 4 properties. What are the properties if you look like? So the first one is that likely events have low information. Unlikely events have high information. The third thing is that likely events have less information than unlikely events. The fourth is that if unrelated events are there, The total information is the sum of the individual information values. So you have two unrelated events. The total information is nothing but the sum of individual information values. So, for example, so in a normal conversation, you cannot have completely unrelated events. If I say, today I ate a big pizza, or today I can say that today I ate a big sandwich, but I cannot say today I ate a big bathtub, or I cannot say today I ate a big sailboat. When I say today I ate a big, which means that it should be followed by some food items. It cannot be other items. So in normal conversation, we cannot have completely unrelated events. If unrelated events are present, they are given by the sum of individual values. Next, we will see about the so the amount of information is usually influenced by the size of the probability function. So the number of words can affect the, in other words, I can tell the amount of information is influenced by the size of probability function. In other words, I can tell it as the number of words are usually affected by the amount of information. I can give you an example for this. You have a sender, you have a receiver. You have to send a book to the receiver. So how are you going to send this book is that for every word in this book, unique words in this book, you assign a value. For I can assign 0 for the, 1 for and, like that, you create a word list. So this word list will be shared between sender and the receiver. And then instead of sending the complete book, you send only the quotes to the receiver. So the global context between the sender and the receiver is the word list. And how much quotes you are sending. So it depends on the number of possible words. So the number of possible words affects the amount of information to be sent. Is it clear? So now let's look into so now you look into adaptive quotes. So the sender and the receiver should share a context to adapt to their transmission. This is clear from it. For example, if you have a common context called orchestral music, if the context is music, then if I use the terms called violin and tabla, then it is common. If I'm using terms like starfish or octopus, then it is not common. But if I'm using an context called underwater exploration, then all these sea animals will be common. So in order, we should use this observation to improve the efficiency of sending our messages. The greatest example for this one is Morse code. Anyone would like to tell what is Morse code? Would anyone like to tell what is Morse code? So, yeah,
Where they use dot and dash as a language, and they
fantastic. Yeah. So each typographical character has an associated pattern of dots and dashes. For example, A can be written as, sorry, can be represented by dot and a dash. B can be represented with a dash, three dots. C can be written as dash dot dash dot. D can be written as dash dot dot. E can be written as dot. So like that for all the alphabets, we have uh, the pattern of symbols. So each dot is a short burst of sound. So these are not these are not writings, but it is a sounds. So this is a short sound. This is a long sound. So the length of duration uh, used to represent a small dot is called as dit. Dit is the unit for the length of time used to hold the dot. So a dash takes the length of three dits. Between the letters, there is a silence of three dits. And there is a silence of seven dits between the words. So Morse code was traditionally sent by using telegraph keys to enable or disable the transmission. So it has three types of symbols. One is dot, the other one is dash, and the other thing is dot sized spaces. So it has three symbols. So suppose if I want to write nice, how can I write it? So N is given by a dash dot. So between letters, there is three dit-sized spaces. Next, I have to write I. How can I write I? Two dots, then three spaces. Then I have to write C. C can be written as dash dot, then three spaces. Then E is written by one dot, then three spaces. So this is how we send it. So these are all tones. This dot is a short tone, dash is a long tone. And we saw the length of dots and dashes. It's a great way to send the messages across noisy telegraph because the tone could be made of even the presence of the because it could be made out even in the presence of the uh, noisy environment or noisy interference. So how Morse code distinguishes two symbols is that it is by their duration. So it will listen to the length of duration. So based on the length of duration, it will identify different alphabets. So instead of having different duration, we can also have same duration. So we can use dot for low frequency and we can assign high frequency for dash. So R can be written as dot dash dot. So this can be represented by low frequency, high frequency, and low frequency. We can send it in this way also. There is also one more way where all the alphabets will have same number of symbols. That is also possible. But this is interesting to learn. This is not about deep learning, but it is interesting to learn how they framed the Morse code. We all know that the alphabets are in this order A, B, C, D, E, F, G. But Morse code follows a letter frequency table. E, T, A, O, I, N, like this. So this is the order which is followed by the Morse code. Why they are following this order is that E is the most frequently used letter in the English language. Second most frequently used letter is T. So E they represented with a single dot. T is the second most frequently used alphabet. So they use dash. So these are single letter symbols. Sorry, single letter pattern. Next A is given as a dot and a dash. From A till M, they use two letter pattern. followed by that, they have 3-letter pattern. So this is how they have framed the Morse code. So they are following the letter frequency table to develop it. Just a little bit of history. In this original code, we introduced Morse code, but he defined the pattern only for numbers from 0 to 9. But later on in 1844, there's a person called Alfred Vail. He only introduced Morse code for letters and punctuations. So why are we learning about Morse code itself? We need to know about the coding, different coding patterns. So that is why I gave this introduction. So now we will come into information theory. So what is adaptive coding? Adaptive coding is, here we saw it has a 2-letter code, single letter code, 2-letter code, 3-letter code. In adaptive coding, we have a dynamic method of encoding. Encoding means we assign a code value for a alphabet or a letter, sorry, alphabet or a number or punctuation. So we are encoding, instead of E, I will use a dot. So similarly, we can have several codes. So when we are transmitting, if we are dynamically assigning the encoding scheme uh, for the data, then it is called as adaptive coding. It refers to the dynamic method of encoding data, where the coding scheme is just adjusted on the fly based on the data being processed. So it is commonly used in data compression. It is used in data compression so that we can reduce redundancy. It is also used because it is effective in storage and transmission. There is another type of coding called as variable bitrate coding. Variable bitrate coding means, based on the complexity of the data, we will vary the bitrate. Suppose if you use there is also another coding called constant bitrate coding, where we will use fixed number of codes for everything. But variable bitrate means, based on the complexity of the data, we can change the bitrate. How to say an example is that, suppose if you are sending a video, the video has lot of frames. So video has lot of frames. So frames contain lot of motion, then we can have a higher bitrate for it. If the frames have static pictures, then we can keep a lower bitrate. If you are transmitting a song for high frequency, we can keep high bitrate. For silence or low frequency, we can use lower bitrate. So that is how this variable bitrate coding is used. Next, we will see about the popular coding method called as Huffman coding. Huffman coding is popular in data compression technique. It's a popular algorithm used in data compression techniques. It uses for more frequently used symbols. It assigns a shorter code. For less frequently used symbols, it assigns a longer code. By assigning in this way, it minimizes the total number of bits required to encode the data. Is it clear? So we started with adaptive coding. To understand what is coding, we saw the example of Morse code. So Morse code assigns based on the frequency table. So based on the frequency letter table, it assigns the pattern to the alphabet. So the most frequently used things have shorter symbols, so shorter codes. The less frequently used symbols have a longer codes. Then we saw about adaptive coding. Adaptive coding is used to reduce the redundancy in the data compression techniques. So it adapts on the fly. So based on the data which is present, it changes the code every time. Then we saw what is variable bitrate coding, constant bitrate coding, and Huffman coding. Is it clear? Okay. Now let us see what is entropy. So entropy is nothing but the amount of information or uncertainty in a random variable or a probability distribution function. So amount of information is entropy, or amount of uncertainty is called as an used to quantify unpredictable or disordered information. Suppose if we have a discrete random variable, say x, the outcomes can be given as x1, x2, xn. Their corresponding probabilities can be written as p of x1, p of x2, up to p of xn. The entropy is given as h of x. So h of x can be written as minus summation I is equal to 1 to n, p of xi, log of p of xi. This log is to the base b. This log base is 2 or natural logarithm e. So this is the formula for entropy. So h of x, nothing but it represents the average number of bits needed to encode the information. We saw bits is the unit of information, and we also saw what is encoding. We also know what is information. So the average number of bits needed to encode the information is given by entropy h of x, and that is calculated from the probability distribution function. So x is a discrete random variable. If the outcome of an event is given, if you have n outcomes of an event, then their probabilities are given by p of x1, p of x2, p of xn. Then the entropy is given by this formula minus summation of. So since it is discrete, I'm using summation symbol. If it is continuous, then I will use an integral. Is it clear? So entropy is a very important concept in information theory. Entropy is nothing but the amount of information or amount of uncertainty present in the random variable or in the probability distribution. Next, we will understand what is evenly distributed or even distribution. Evenly distributed distribution means all possible outcomes of a random variable are equally likely. So it has two properties. The first property, when you will say a probability distribution is evenly distributed, means when all has the same probability. For tossing a coin, you have probability of getting a head is also 1 by 2. Probability of getting a tail is also 1 by 2. So the probability of both the outcomes are same, are equally likely. I shouldn't say same, it is equally likely. So then in that case, you can call this event as evenly distributed event. So the first property of evenly distribution is equal probability. So P of xi is equal to 1 of n, or I is equal to 1, 2, up to n, where n is the total number of outcomes. Secondly, it uses maximum entropy. Why I am saying maximum entropy? What is entropy? It is the amount of information or the amount of uncertainty present in the random variable. So when all the outcomes are same, when the probability of all the outcomes are same or equally likely, then the system is unpredictable because all the outcomes are same. All the probability of all the outcomes are same or equally likely. So the system is unpredictable. If the system is unpredictable, which means that uncertainty is high. When uncertainty is high, entropy is also high. So evenly distribution means it has two properties. The first is it has equal probabilities for their outcome. The second one is that it has maximum entropy. So that is one you have to, next time when I say evenly distributed, you should remember it has these two properties. So now let's go back to our entropy. So we will interpret our entropy. So entropy can be high, low, or zero. The amount of information or amount of uncertainty present in an event can be high, low, or zero. When we will have high entropy? Imagine that when all the probabilities are evenly distributed. So the probabilities of all the outcomes are same, 1 by n. Then it indicates high uncertainty or unpredictability of the data. So in that case, we will have a high entropy. Let's derive this and see how it comes. So let's take an example. We are tossing a fair coin. So when we are tossing a fair coin, the probability of getting a head is 1 by 2. The probability of getting a tail is also 1 by 2. So we know the entropy formula. H of x is equal to minus P of x summation minus P of x log of P of x. Xi. I is equal to 1 to n. So we have two probabilities. This is first probability. This is second probability. So how I can expand this? So let me expand. There are two. So I is equal to 1 to 2 P of xi log of P of xi. So P of h, I am writing it as P of x1. Instead of h, I am using the variable x1, which is 1 by 2. P of t is, I am representing it as a second event, second outcome as x2. So instead of t, I am writing it as x2, and that is equal to 1 by 2. So how I can expand this one? H of x is equal to minus P of x1 log of P of x1 plus, you have another minus here, P of x2 log of P of x2. So now we can substitute, we know the value of P of x1 and P of x2. So we can substitute these values, 1 by 2 log of 1 by 2 minus 1 by 2 log of 1 by 2. How I can write 1 by 2? 1 by 2 can be written as 2 power minus 1. So minus 1 by 2 log of 2 power minus 1 minus 1 by 2 log of 2 power minus 1. So this minus 1, I can, whichever is in the here, I can put it before. So then you will have 1 by 2 log of, this is log of to the base 2. So here also you'll have 1 by 2 log of 2 to the base 2. Log of 2 to the base 2 is 1. So you have 1 by 2, 1, 1 by 2, 1. This is nothing but 1. So h of x is 1 bit. The unit of entropy is bit because we are measuring the amount of information or amount of uncertainty. Since it is an amount of information, the unit of information is used for entropy also. So h of x is 1. It has a maximum value. So we have probability. So when we have higher probability, when we have the probabilities of outcome to be equally likely, then we will have a higher probability. So next we will see when we will have low entropy. Suppose if we are using a biased coin where we will get a heads all the time. So probability of x1 is going to be 1. Probability of x2, we are not going to get tail at all. We are always going to get head. So then p of x1 is going to be 1 and p of x2 is going to be 0 always. So in that case, I'm rewriting this one by substituting in this formula. So if I substitute here, we'll get minus log 2 of 0 plus 1 log of 2 to the 1. So 1, I can write it as 2 power 0. Anything to the power 0 is 1. So instead of this place, I will use 2 power 0. So this one is 0 multiplied by something is 0 plus 1 log of 2 power 0. So this 0 will come in front. So you will have ultimately 0 as your answer. So this has a low entropy. Then, so one event is highly likely. When one event is highly likely, there is no uncertainty here. When the uncertainty is less, we have low entropy. That is what we have to understand. Then we will have zero entropy. Suppose if the outcomes are deterministic. So the outcomes are deterministic. There is no chance for uncertainty. Then we will have entropy to be 0. Because no uncertainty or no information is gained by observing the outcome. So our entropy would be 0. So what we saw so far now is that we saw the important concept in information theory, which is entropy. Entropy is nothing but the amount of information or amount of uncertainty. It is given by this formula. And we saw what is evenly distributed variable. And we saw 3 different interpretations of entropy: high, low, and 0. Is that clear?
Yes,
Is it clear? Okay. Yeah, we will see the rest of the things in the next class. Any doubts for anybody?
Ma'am, low
Anyone
entropy
has-
also is 0.
Have some other values also. But for simple understanding, I gave this example. Low can be 0 also.
Okay.
See, anybody needs any clarification for anything? Okay, if not, we will see in the next class. Next class will be on Monday.
Sure, ma'am. Thank you.
Thank you.
Thank you, ma'am.
Thank you, ma'am. Thank you.
Thank you, ma'am.